both in a way, as I said, both those linear terms for the electric field, where there is only linear term, at least in that gauge which we have chosen, being the Coulomb gauge, and for the external magnetic field, there is this linear term. They are sort of classical, and we could have written them down or postulated that they look like this just from classical electromagnetism. What is now not classical at all is this extra term, this squared term. Where is it? There, this one. That is something which you don't have in classical electromagnetism. So let's look at that. And again, with the external magnetic field, and I think Frank calls it H2 psi. And that's E squared divided by 2me, sum of all electrons, and then the vector potential at the position of the electrons squared. And if I insert now the expression for the vector potential here, I get, in the first place, I get E squared divided by E squared divided 2me, sum of I, and then I get 1/2 B cross Ri minus Rg. And in the square, that's the scalar product. So it's, let's put a parenthesis like this, times the same thing once again. Like this. Now the 1/2, that's easy. I can take that out, which gives E squared divided by 8me, sum over I. But what I now have, I have a scalar product of two cross products. And again, if you had some electromagnetism or electromagnetism course, you might have seen expressions like this and how you can rewrite that. You can rewrite that to something which looks like this, where we now get, let's see, yeah, put a big parenthesis. I get a magnetic field, one of them, and then I get a parenthesis, and I get this Ri minus Rg transposed times Ri minus Rg minus the other way around, Ri minus Rg times Ri minus Rg transposed here. So one is the inner product, the other one is the outer product. B. And then of course what I can do, well, never mind whether B is out there. I could put the parenthesis actually also here. What I can do, I mean the B field, they don't depend on the electron index. So I can move the B field out. And I can at the end then write it as B dot, and now I want to have a parenthesis, and that's like this, sum over I, and I have the E squared divided by 8me in here, like this. That's B and B. That's the field. And you can see all the other operators like this one, but also the ones we had before, I mean, they are contributions to the Hamiltonian coming from the field, so that's what we call the perturbation operators. But they all split up in two terms. They split up in the fields here and also here, and then a part of the operator which depends on the electronic coordinates here, because here you have the electronic coordinates in here, or here because in the magnetic dipole moment operator you have the angular momentum operator of the electrons. So you can separate it in a part which is the external field and a part which depends on the electrons. And that's really in a way important for us later, because remember we want to define properties as being derivatives of the energy with respect to the fields. And therefore it's really handy if we wrote all the operators nicely separate, a part which depends on the electrons and a part which only depends on the fields, which wouldn't be a bit difficult to do here, so it's much nicer to write it in this way. Right, and I think I think Frank might actually call that operator something with P, that part here. P2, something like this. So that's with an external magnetic field. And that's the part where you have the field squared. Now that was only this one, but we also have this one here. And that's the interaction with the nuclear magnetic moment. So this situation is we put a molecule alone in a magnetic field, and look how the energy changes of that. And we will get sort of induced magnetic moments from that. And there is a property which is the analog to the polarizability, which is it's called the magnetizability, and which is the proportionality constant in the induced magnetic moment. So it's precisely the same story as for the polarizability and the electric dipole moment. You can write it up for the magnetic dipole moment and in the presence of the magnetic field, and then you get a property which is called the magnetizability, which is a second derivative of the energy with respect to a field, or twice a field. And there this term comes in, because this is quadratic in the magnetic field. So that's a contribution, will give a contribution to the magnetizability.